Alright, so the topic for today is equivalent statements. And what do we mean by equivalent statements? Well, what I mean by that is a statement that conveys literally the same meaning or the same information. And actually, the truth table is not only useful for determining whether or not an argument is invalid or valid, but the truth table can also determine if two statements are equivalent to each other or not. And so let's just start off with an example, okay, like we always do. So we're gonna let P stand for any statement and Q stand for another statement. And it doesn't really matter what P and Q means, and I guess you can use your own imagination to like assign each of these letters a meaning on your own, but really it doesn't matter, and that is because uh, it it's not gonna affect how we're gonna build the table, right? If we have P and Q and we make a truth table for that, like it doesn't matter what P means, it doesn't matter what Q means, the logical relationship should still be the same. So let's start with the truth table. Let's start with P and Q here. And we will have 4 different realities. And, just, the drill, right? It's true, true. So both P and Q are true in the first universe. Whatever P is, whatever Q is, it doesn't matter. You can assign your own meaning to them in your own head. I don't really care. Second reality, true, false, false, true, and false, false. So if we have 2 statements, there are 4 different possibilities. Alright, now I'm going to make a claim here, okay? I'm going to claim that this statement, P and Q, and this statement over here, not P or not Q, I'm going to claim that these 2 statements are equivalent. So let's say you assign a meaning to P and a meaning to Q, right? So if you did that and you translate this statement back to your own language, however way you assigned it, and if you translate this one also, you're going to get the same statement. Well, it won't be the same statement exactly. It might be shuffled around a bit, but the essence is that the meaning of these 2 statements are equal and the same, and they convey the same information, basically. So, how are we going to use the truth table to prove it? Well, all we have to do is show that these columns over here are going to be equal to each other. So if this one is F, 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 then this one should also be F, 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 and only then are they equivalent. So basically they have to be exactly the same. And once we prove that, then that's it. We have proof that these 2 statements are indeed equivalent to one another. And so let's try and do that, shall we? Well, let's do a truth table for this guy first, the inside part. And then after we do the truth table for this guy, what we're going to do is we're going to flip it around because we have this not statement over here. This not statement, it acts like a reverse switch. And I've already shown you an example of this in the previous episode, so it should be familiar to you, the process and the pattern. Alright, so P and Q, right? So this one should be the only one that satisfies both of them. Alternate reality number 1. So this should be true and the rest should be false. But what did we say over here? We have a not statement. That means not P and Q, which means essentially what we have to do is just reverse all of this. So if it's not P and Q, then our statement over here, which originally showed P and Q being true, should be reversed, because we don't want P and Q to come true. So that turns into an F, this turns into a T, this turns into a T, and this turns into T, for the same reason that we flipped number 1 around. Alright, what about this one over here? Well, let's make the truth table for not P and not Q individually, and let's just do that on the side here. Not P and not Q. So if P is true in universe number 1, then that means not P should be false. And same deal, we just flip all of these around and everything should just make logical sense. So whenever P is true, we have to flip that around. And whenever P is false, we also have to flip that around to turn it into a true statement. And same thing for Q, we have F, T, F, and T. Alright, so now let's use what we have over here to build what we have over here. So this is an OR statement, which means we only need one of them to be satisfied. So all of these guys are going to be true, while the top part over here is going to be false, because it doesn't satisfy both conditions. So what we have here, we have two columns that are exactly the same to one another, and this indicates that the two statements are equivalent. And it's easy to argue why, because remember, each row represents a separate universe. So in universe number 1, this statement is false. Likewise, this statement is also false. In universe number 2, whenever this statement is true, this statement is also true. So it doesn't matter which alternate universe you are in, these statements are always going to be equal to one another. And these are all the possibilities. These are all the cases, by the way. So it has to be that these statements convey the same meaning in order for them to be true in all possible scenarios, right? Just makes sense. And this over here, it may not be a satisfying proof. So let's try to prove it linguistically, alright? Or through language. So let's just assign a meaning to P and a meaning to Q, just so we can translate them to the English language, because everything is just computer logic, math kind of stuff here. So let's let P become, let's let P be Peter went to Starbucks or something, and Q is the Queen of Elizabeth went to Starbucks, right? So universe number 1 is where, did I say Peter? Yeah, I think I said Peter. Peter and the Queen went to Starbucks together. And universe number 2 is only Peter went to Starbucks, and so on and so forth. So these are all the possibilities here. So let's translate this statement over here. Let's translate this to the English language, right? So what's inside over here, it basically means Peter went to Starbucks and the Queen went to Starbucks. So both Peter and the Queen went to Starbucks. But we have a no over here. So basically, so to convert this into the English language, Peter and the Queen did not go to Starbucks. And let's move over to the second statement and try to convert that into the English language. So not Peter and not Queen. So this basically means Peter did not go to Starbucks, right? And this statement over here says that the Queen did not go to Starbucks. So to translate this, basically it means either Peter did not go to Starbucks or the Queen did not go to Starbucks. And these may seem like two different statements, but they're actually identical. And you might not see that at first. It might not be obvious, but let's try to explain why. So let's just say that you went up to a person and this is what they said. Statement number 2. Either Peter did not go to Starbucks or the Queen did not go to Starbucks. So if we look at our truth table here, which is basically like the book of creation, it's all possibilities. So the Queen did not go to Starbucks. And well, that's true in universe number 2. So let's give that a check. And Peter did not go to Starbucks. Well, that's also true in universe number 3. So let's give that a check as well. And since this is an OR statement, it allows for the possibility that both Peter and the Queen did not go to Starbucks. So let's give a check to number 4 here. So to recap, when the person says either Peter did not go to Starbucks or the Queen did not go to Starbucks, it tells you that either you are in universe number 2 or universe number 3 or universe number 4. You can't be in universe number 1 because Peter and the Queen both went to Starbucks there, right? And if you were in universe number 1, then the guy that we talked to earlier was lying because the guy said that Peter did not go or Queen did not go. So if both of them went, that means that he is lying. But let's just assume that this person is not lying. Let's just say it's an all-knowing computer or an all-knowing God. So it won't lie to your face. And so the information that this person conveys is that you're in either universe number 2 or 3 or 4. That's the sort of information. From talking to him, you know that you're in either one of these universes. Alright, so what happens when you talk to a person and let's say instead of they saying statement number 2, they said statement number 1 instead. So they said Peter and the Queen did not go to Starbucks. So both of them did not go to Starbucks, right? So it tells you that you're not in universe number 1. And that just leaves the other 3 universes as a possibility. And no matter what the person says, if the person said statement number 1 or if the person said statement number 2, both of them, even though these are different statements, convey the same sort of information. It both told you that either you are in universe number 2 or universe number 3 or universe number 4. And because they convey that same meaning or that same information, they are equivalent statements. They mean the exact same thing because all the scenarios just match up together in all different possible cases, in all different possible universes. Everything matches up. So the only way that that is possible is if these statements are somehow equivalent. And before we finish off this video, let's talk about applications a bit. So why do we have to study equivalent statements? What is their purpose? Well, one thing that they can do is they can simplify statements altogether. So earlier in this example, we noticed that this statement over here is equivalent to this statement over here. And it doesn't matter what meaning you assign to these statements, no matter what your imagination has planned for you. If you assign P a meaning, if you assign Q a meaning, and if you make a sentence with this structure and this structure, no matter what you assigned the statement to be, they are going to be equivalent no matter what. Because, so Peter here and the Queen here and them going to Starbucks, that has nothing special to do with this truth table, right? It does not affect the truth table in any way. So if we change Peter and we change the Queen and we change Starbucks or whatever, it's not going to change how we build the truth table. P and Q, like I said at the beginning, it doesn't matter what you assign to them, and they just have this arbitrary meaning. So let's write this equivalence down. Not P and Q is equivalent to not P or not Q. And this is true for all P and Q. So whatever statement, whatever meaning you assign to them, it will be true, like I explained before. And like I said, we can use this to simplify statements. Let's say you're writing a book or you're writing an essay and there is just one sentence that you don't quite like. So what you do is you translate your statement and you give symbols to them and then you just express them like this. So like we did before. Like what we did over here before, except it's in the opposite direction. We started with our statement and then we translated it to English, but we can just do it the other way around as well. We can start with English and translate it to this logical computer science language. So that's what you do. You translate your sentence into computer language, and this is what you get. So you have a sentence or whatever from the book that you're writing, and then that translates to this statement over here. Now, how are you going to simplify it? Well, this looks awfully similar to what we have here, which means we can convert it into this thing somehow. But it's not exactly the same. What you can do is you can perform a sort of substitution. So you have a statement, not Q, and you set it to be equivalent to another statement, C. And remember, these are just statements, so you can just make them up. So this basically means the Queen did not go to Starbucks. But who is out there forbidding you to create a new statement? So that's what you do. You create a new statement, right? And then you call it C. And what meaning do you assign to it? Well, I assigned the meaning, the Queen does not go to Starbucks. And nobody's stopping you from doing that. So you have these two statements, and they're equivalent to each other because you gave them the same meaning. And this just turns into not P or C, because this and this has the same meaning, and you made sure that that's possible because you assigned the meaning to this guy and this guy yourself. And now this looks similar to that, right? And since we have already proven that these two statements are equivalent, then we can just perform the simplification. So this guy turns into this guy. That just means not P or not C, right? So we're just using what we have on the top over here to get from this row to this row. Alright, so we don't want C, right? Because Q is our original statement. So what we can do is we can convert it back to not Q again. So we have not P, or remember this not is still there, okay? And we're just converting the C into not Q. And what we end up with is not P or not Q. Now, this seems complicated, but not Q is actually equivalent to Q itself. Because remember, not just means that you're flipping the statements around. So if Q has the table TTF, then not Q flips it around, right? So you get FFT. And if you add another not to that, then it flips it around again. So F just turns into T, and F just turns into T, and T just turns into F, and you have the same columns. And by what we just learned before, since these two columns are equivalent, this statement over here and this statement over here is equivalent, meaning we can simplify this statement further again into just being not P or Q. So we went from this complicated looking thing into something more simple. Now what do you do after this? All you have to do right now is to just simply translate this back into another sentence. and these two sentences will convey the same meaning, but they will have different structures, like what we have in statement number 1 over here and statement number 2 over here. So this is a really good way. I mean, I don't know why you would try this unless you are like really try-harding your essay or try-harding writing your book. I don't think I'd ever use this myself when writing an essay or writing a book, but if you want to change a sentence because you don't like it, then I'm just saying you can use a truth table to do that, and I just think that it's interesting that you have this option. And yeah, that's it. That's the end of the video. It's a pretty short one, but hey, there will be lots more to come. So I hope you stay tuned.